We are making hopefully best large language model in the world, and it's fully open source, and we will document all of the entire process. So I got this train LLM that is the full large language model code, and I also have this train distributed LLM. So this is the first one is just one GPU, and the second one is distributed over many GPUs. So we need to figure out how to actually fix this, if there are any bugs in distributed training, and how to run the distributed training over more GPUs. I will launch 2 GPUs on Novita AI, and if I choose here 50% off, I'll just take 2 of these, 4090, and it's 36 cents per hour. I think it's very good. Link below. First, I want to run both of these single and distributed training to see if the distributed is going to train 2 times faster. And I told that here to Claude or to Cursor, I don't know which model, and then it checked. I'm going to see what it did. We'll train for 5,000 steps in 1 GPU and half of that training steps on 2 GPU, so they see same amount of data. So GPU is 100% processing utilization, but memory just 40%. This is not good, but we'll figure this out. I just want to see what we have by now. We are measuring time to process the same total amount of tokens, and total tokens is maximum steps times batch size. So we have same batch size on 2 GPUs times maximum length times world size. So we will cut just max steps by 2 because we have 2 world size when we have 2 GPUs. Everything else will stay the same. 2 GPU training finished. I'm gonna copy that, give it to AI here, and I'm gonna also run 1 GPU training, so this should run 2 times slower. There is a bunch of text. I'm just gonna ask Cursor what this text means, and I copied it. So now only 1 GPU is utilized, and it's just, okay, it's 95%, 99, 98, okay, that's good. Memory, so low, what's happening here? 47%, that's it. The same memory as before, so I guess, yeah, the same thing. I'm using this GPU monitor to monitor GPU in different terminals. I have 2 terminals. One is training, one is monitoring. So I finished, and the results are quite good. We almost got double speed improvement. 92% I think is pretty good. These are the results. So 1 GPU, 16.8 steps per second. 2 GPUs, 15.47 steps per second per GPU. So in total 30.9 steps per second. I did not expect this to work so well because this was distributed by Claude. I didn't even code too much here. So now we will just keep understanding this and improving it. This shows very good scaling and efficiency for distributed data parallel. I can pause GPUs for now, just stop them because I'm gonna be understanding now. So how did we do this distributed training? Distributed data parallel is PyTorch's recommended approach for multi-GPU training. It enables training large models by splitting data across multiple GPUs while maintaining synchronized model weights. So we copy model onto both GPUs and send data to both of them. So before training begins, we first need to give rank to each GPU. It's just its ID. The first GPU gets rank 0, the second GPU gets rank 1. World size is the number of GPUs, default 0 for example. Local rank, the GPU ID on the current machine. I'm not sure how we use this. I'm not sure what this is. Then we assign each of the processes, different processes to different GPUs. I guess process is the whole model and the data. DDP processes communicate using a backend protocol. NCCL, NVIDIA Collective Communication Library, is optimized for GPU to GPU communication, enabling efficient gradient synchronization. So we use this NCCL. Here, initialize process group, dist.init process group, NCCL. And this dist is just imported from torch.distributed. The key to DDP's efficiency is that each GPU processes different data. Train sampler is distributed sampler, and pass in train dataset, shuffle true, drop last true. What is this? Anyways, then we define train loader, data loader, again train dataset, batch size 24 in our case, and sampler will be our train sampler. So distributed sampler ensures each GPU gets a unique subset of the data, no data overlap between GPUs. Together, all GPUs cover the entire dataset. How data is split? For a dataset with 1000 samples and 2 GPUs, GPU 0 processes samples 0, 2, 4, 6, GPU 1 processes samples 1, 3, 5, 7, and these indices are implemented in this line. So, how model is replicated? It starts on one GPU and is replicated to the other ones. So model is equal to minimal model, pass in the config, dot to device to GPU. And then for param in model parameters, we're gonna broadcast all of them to the other GPU. So this dot broadcast param detach 0 and maybe default. This ensures all GPUs start with identical model weights. It's gonna just copy them. The model is wrapped with DDP to handle gradient synchronization. So model is equal to torch NN parallel distributed data parallel, wrap in model, device IDs is gonna be local rank, which is still weird. Local rank is a GPU index on the current machine node. So if we have maybe 8 GPUs on a node, and then we have some number of nodes, then local rank is the index on that node. It's different from global rank, which identifies processes across all machines in a distributed setup. Each GPU will compute its own forward pass, no communication yet. And then backward pass with gradient synchronization, so automatic gradient averaging. The magic happens during backward propagation. Loss.backward, DDP automatically synchronizes gradients. Behind the scenes, DDP computes local gradients on each GPU, initiates all reduced communication, averages gradients across all GPUs. Each GPU ends up with identical averaged gradients. So I guess it sums up all of the gradients and then divides by the number of these GPUs, and then pushes that to every single GPU. So it's synchronized. So this is what all reduce or average does. We have gradient A is 2, gradient A is 3, but on different GPU. Now both of the same gradient will be 2.5 on both GPUs. So optimizer step will make identical updates to weights. Result, all GPUs maintain synchronized model weights throughout training. So every GPU will process same number of batches. So it will divide batches to each GPU and drop all of the remaining batches. So this is integer division. If we have this self.drop_last. We have this dist.barrier at 4 times in our code. 4 places. It will ensure all processes reach the same point here. Wait for all GPUs to reach this point. Each GPU manages its memory independently. So if it empties cache happens on each GPU independently. In my last video about theory of LLM scaling, we saw that Hugging Face actually splits a single model onto 2 GPUs. We are copying model to every GPU, but they split one model to 2 GPUs with Tensor Parallelism. The difference, so in our current case, we have a GPU 0 full model, processes batch A of data, GPU 1 full model, batch B of data. But in Tensor Parallelism, we have GPU 0, we have first half of the model, same batch, second half of the model on the other GPU, same batch. So this batch enters here and continues to this GPU. The most common approach is splitting weight matrices. So original layer can have some this weight, this matrix, and then split this second dimension. I saw DeepSeek using this. Maybe we'll use this, but let's go with data parallel for now. This is we will use this maybe later. Of course, DeepSeek is using this, everybody's using this, I think. That will be it for this video. In the next video, we will do research on attention mechanism. We're gonna try our current full attention versus grouped query attention. So check the video below. The playlist, I'll put it in a playlist.